In this short video lesson, we are now going to look at the second type of radioactive decay, namely beta minus decay. Now, this is more complex than alpha decay. In this particular process, there's the emission of an electron from the nucleus, which is strange because we know that in a nucleus of an atom, there are just protons and neutrons. So where does this electron come from? Well, if we look at the general equation, and we're looking at it from a particle perspective, elementary particle perspective, then one of the neutrons in the nucleus, which we represent with a mass number of 1 and an atomic number of 0, because it doesn't have a proton's charge, then it decays into a proton which because it's a nucleon has a mass number of 1, and it has a +1 charge, so we view that as the atomic number. So we've got the mass number and the atomic number. You're going to see it's going to be a bit strange soon enough. Then this is a positive particle, note the +1 there. Here we have an electron, and an electron does not have a mass number because it's not a nucleon. It's neither a proton nor a neutron. But we say here that in the place of the atomic number, and this is where it gets a bit weird, we put a -1. And that denotes that it has an opposite sign charge to the proton. So it's kind of an atomic number in apostrophes. So this is the beta minus particle, which we can also write as 0, beta -1. And we've come across this before. This is an anti-electron neutrino. And so what is happening here is a neutron decay. If we look at the general equation from a overall nuclear perspective or nuclide perspective, then we have a nucleus that has a mass number A and an atomic number Z. Now, taking into account what's happening here, one of these nucleons is decaying into a proton. So the atomic number is going to increase to +1. Right, now this proton is not going to be ejected out of the nucleus. It's going to remain in the nucleus, so it adds to the atomic number of the nucleus by 1. But by doing that, the element changes from X to Y, so this denotes a different element. But because a neutron has become a proton and both are nucleons, the mass number remains unchanged. Now, we have the beta particle and we have the electron antineutrino. That's what that bar is on the top. That's for the antiparticle. If we now look here and we see, okay, on the left-hand side, there's a mass number of A. On the right-hand side, A + 0 is A. So the baryon number is conserved. The mass number is conserved. If we look at the atomic number is not actually conserved. If one views the atomic number as the number of protons in the nucleus, then we see that on the left-hand side we have Z protons. On the right-hand side, the daughter nucleus now has got 1 extra proton, so that's Z +1, which means on the periodic table, the element is going to shift from left to right. So it'll be the next element on the periodic table to the right in a particular row. So now, if we look at the beta particle, we know it's got a -1 charge, and there's the electron antineutrino, which doesn't have a charge. So looking here, if you look at the negative 1 here, if you add it to this, z plus 1 minus 1 gives us z, then you get a balance. Z equals z plus 1 minus 1, which equals z. But the atomic number is not conserved because the number of protons increases. But what is conserved is the charge. So the charge of this nucleus would come from the amount of protons. The charge on this side, the charge has gone up by plus 1, but on this side, the beta particle has a negative 1 charge, and remember, plus 1 denotes plus 1,6 times 10 to the negative 19 coulombs, and negative 1 denotes the charge on an electron, which is negative 1,6 times 10 to the negative 19 coulombs. So plus 1, negative 1 actually cancels out. So here on the bottom we see not the conservation of atomic number, but the conservation of charge. So an example of this is radiocarbon dating, which I'm sure you've heard of, which involves carbon-14, the carbon-14 isotope. So carbon normally has a mass number of 12, but radioactive carbon has 2 more neutrons than the normal carbon, if I can use that term. And so what happens is there is a beta particle that is emitted and an anti-electron neutrino. Looking here, the mass number doesn't change, but one of those neutrons here becomes a proton. So the atomic number goes up, so from 6 to 7. Mass number stays the same. We know the beta particle, or the beta particle, depending upon how you want to say it, has got a charge of negative 1 because it's an electron. It's not an orbital electron. This is an electron that has come out of a neutron decaying. Quite an amazing process. So if we look at the charge, we would have plus 6 on the left-hand side with the parent nucleus. With the daughter nuclei, or daughter nucleus, we'd have plus 7. But the beta particle has got a charge of negative 1, so negative 1 plus 7 gives us plus 6, which was the original charge of the parent nuclei. So now, looking at the properties of beta minus radiation, and this is very important, this is something we can ask in a test or an exam. The particle nature of this type of radiation is that an electron, normally quite a high energy electron, is emitted, and an antineutrino, an anti-electron neutrino. The charge of the beta particle is negative E. The mass is 9,1 times 10 to the negative 31 kilograms, which is in actual fact the mass of an electron. When we look at interaction of the beta minus particle, it collides with other electrons, roughly 100 ions per millimeter of air for 2 megaelectron volt particles. The range is approximately 30 centimeters of this form of radiation. So if you think of how small an electron is, it comes out of the decay of a nucleus, it can travel up to 30 centimeters. That is a huge distance when looking at it relative to the size of the nucleus, 10 to the minus 15 meters, out of which it comes. The penetration is higher than that of an alpha particle, up to about 1 millimeter of aluminium. The ionizing ability to ionize the air, it's pretty low, and it's detected by Geiger-Miller tubes or Geiger-Miller counters, cloud chambers, photographic paper, and it too is affected by electric and magnetic fields. Now we look at the beta plus decay, which is the inverse. In this process, a proton decays to become a neutron, a positron, and an electron neutrino. So the general equation when looking at just the specific particle, elementary particle, that's decaying, we've got a proton which has a mass number of 1 and an atomic number of 1. It produces a neutron which is neutral, and we look here now and we see that it has an atomic number of 0. Obviously neutrons don't have a positive charge, they're not protons. Here we have a anti-electron. So we have a positive electron, which is a positron. It's not a nucleon, so it has a 0 mass number. And remember, this is not really an atomic number. This is more its charge. It's +1, which is the same as the charge of a proton. And then an anti-electron neutrino would be an electron neutrino. So what we have here is a proton decaying into a neutron plus a beta plus particle plus an electron neutrino. If we look at the general equation when working with the nuclei, the parent nucleus is XAZ. Now the proton, one of the protons becomes a neutron. So the atomic number, the number of protons, is going to decrease because now a neutron is produced. But the number of nucleons is still going to stay the same because neutrons and protons are both nucleons. There's a beta plus particle and there's an electron neutrino. Now looking at the mass number, here too, the mass number for the parent nucleus and for the daughter nucleus is the same. The beta particle doesn't have a mass number, so on the left hand side the mass number is A, on the right hand side the mass number is A. So the mass number is conserved, which means that the baryon number will also be conserved. If we look here, the atomic number is not conserved, but the charge is plus Z charge for this nucleus, plus Z minus 1, plus 1 gives us plus Z charge. On the right hand side, keep in mind that the electron neutrino does not have a charge. So looking here, we have a schematic representation or visual representation of what we've been referring to. We've already referred to carbon 14 or radioactive carbon undergoing beta minus decay, producing nitrogen, go from 6 protons to 7 protons because one of the neutrons converts into a proton plus an electron, which is the beta minus particle, plus the antineutrino, the anti-electron neutrino. With beta plus decay, we've got an isotope of carbon, carbon 10, which undergoes beta plus decay. It forms boron, and the reason for that goes from 6 protons to 5 protons, and therefore a positron is produced and an electron neutrino. So if you look on the periodic table, you'll see that boron, then carbon, then nitrogen are found in the same period going from left to right. So here's an example that I would like you to try. I would like you to pause here after this slide and give it a try, and then you can continue with the video to see the solution. So an isotope of hydrogen 3, which in actual fact is known as tritium, undergoes beta minus decay. Determine the daughter nuclide formed. So we know that beta minus decay takes a parent nuclei or nucleus XAZ. One neutron becomes a proton, so there's an extra proton, so it's from Z to Z plus 1 for the atomic number. The actual element changes from X to Y. The mass number is conserved. There's a beta minus particle, a high energy electron that is emitted, and an anti-electron neutrino is produced. So in the case of hydrogen 3, the atomic number is 1. That's what makes it hydrogen, 1 proton. And there are 2 neutrons. 1 proton plus 2 neutrons gives us 3 nucleons, mass number 3. Beta minus decay. 1 neutron becomes a proton, so there's an extra proton, so the atomic number goes up by 1. The amount of particles in the nucleus stays the same. We have a beta minus particle, and we have an anti-electron neutrino. So the daughter nuclide that is formed is going to be 3 helium-2, and that's because when you have 2 protons in the nucleus of an element, that element becomes helium because helium is number 2 on the periodic table, and so the daughter nuclide is the isotope or nuclide helium-3. Here's another one for you to do. Potassium-37 undergoes beta plus decay. Determine the daughter nuclide formed. So beta plus decay takes XAZ to YAZ minus 1. Remember, a proton now becomes a neutron, so the number of protons decreases by 1. The mass number stays the same. A beta plus particle, a positron, is formed, and there is also an electron neutrino. So we have K3719. The number of protons decreases. 19 minus 1 is 18, which makes the nucleus now the nucleus of an argon nucleus, and the mass number stays the same. Beta plus particle, electron neutrino, and therefore the daughter nuclide is of argon 37. So this example or exercise I would like you to do for homework. There's a nucleus XAZ, decays by alpha decay, and then it's followed by 2 successive beta minus decays. Find the atomic and mass numbers of the resulting nucleus. So this is the first of the 2 homework problems I would like to give you. Here's the second of the 2 homework problems I would like you to do. Explain in terms of nucleus structure and stability how unstable heavy nuclides with atomic number greater than 83 may decompose to form nuclides of greater stability. If they are below the band of stability in figure 4.1, figure 4.1 is the number of neutrons versus protons that is plotted. We've seen this before. So from 83 onwards would be going up here, going in that direction. So if the particular unstable nuclide is below the band of stability will continue on. Or how will it decay? In other words, what type of decay? Will it be alpha decay? Will it be beta minus decay? Or will it be beta plus decay, which is basically positron emission? And if they are above the band of stability, then what type of decay would take place in order to achieve stability? At the beginning of the next video lesson, I will go through the solutions and the explanations of the 2 homework problems I have given you, before we then move on to the third and final type of radioactive decay, namely gamma decay, that we cover in this course on radioactivity.